Hello everyone, welcome to this lecture number 35 of the NPTEL course on Riemannian geometry. So last time I proved the first variation formula. So the aim of today's of this lecture is to derive some consequences of the first variation formula, right. So let me remind you of what the formula said. So as usual, gamma from A to B to M is going to be an admissible path, which just means that it is piecewise smooth, and our notation is always that we have this partition A naught up to AM such that gamma restricted to AK minus 1 to AK is smooth, and we also assume that it is regular, which means that either it is the constant path or the velocity vector never vanishes in the smooth regions, right. Alright, and then we also have an admissible variation of gamma. So you should think of this as gamma being a central curve, and then you have this variation, right. So you perturb your gamma through a family of curves, that is called gamma of ST, and our notation is also, we denote this as gamma S of t, right. And we assume that the variation vector field is given by V of t, which is just the derivative of gamma in the S direction evaluated at S equals 0. Then the first variation formula computes the first derivative of the energy functional applied to gamma of S, and it is given by this. So first you have two boundary terms coming from the fact that your variation may not be proper. If your variation is proper, which means that the variation keeps the endpoints fixed, then the boundary terms will vanish because V of A will be 0, V of B will be 0. Then you have a term that comes from the fact that gamma need not be smooth, so there might be jumps in the velocity vector at AK, and then we get the principal term, which is an integral of the inner product of V with the intrinsic acceleration, right. So there are these three types of terms that occur in the first variation formula, and the point is that the energy functional is somehow much more suited to variational analysis because it is not invariant under reparameterizations. On the other hand, the length functional is invariant under reparameterizations, which makes it slightly harder to deal with when it comes to variational analysis. But on the other hand, if you normalize so that the central curve gamma has speed identically 1, then in fact the same formula also holds for the first variation of the length functional, okay. But in any case, I am going to deal primarily with the first variation of the energy functional today, right. So as I said, our aim is to derive some consequences. So in particular, I want to understand what the critical points of the energy and the length functional are. So remember what our end goal is. Our end goal is to try to understand which curves minimize the length, right. That is our end goal. So taking motivation from calculus, in order to find the minimizer of some functional, the first step is to try to find critical points, right. So let me make a definition here. So as usual, omega p comma q is going to be the set of admissible paths from P to Q. Then here is a definition. Let f be a real valued function on this set of paths connecting P to Q. Then we say that a gamma is a critical point if for all proper variations capital gamma of little gamma, if you compute the d by ds at s equals 0 of the script f applied to gamma of s, then that is 0. Okay. So maybe let me just make a remark that you should think of a proper variation are themselves, I mean they themselves can be thought of as paths in the space omega p comma q, right, and why proper variations? Because they keep the endpoints fixed, right. So if you take a gamma which is in omega p of q p comma q, then a proper variation capital gamma will basically keep all these curves in this space omega of p comma q, right. So that is why we need proper variations here. So you should think of proper variations as paths in this space omega p comma q. So a path gamma is said to be a critical point if the derivative along all possible paths in omega p comma q, the derivative at gamma is 0, right, and this is what we understand by a critical point even in multivariable calculus, right. The difference here is that in general this is infinite dimensional. Okay, so on the other hand all our multivariable calculus stuff works for finite dimensionals, but nevertheless one can make a lot of these things carry over to the infinite dimensional setting. Alright, so this is the definition of being a critical point. So for us f is either going to be the energy functional or the length functional, right. Okay, so our main corollary of the first variation formula is the following. So let little gamma be an admissible path connecting P to Q, then gamma is a critical point of the energy functional if and only if it is a smooth geodesic. Okay. So recall that by definition of a geodesic is always smooth, right. So on the other hand a critical point of the energy functional could potentially be only a piecewise smooth function. So part of the claim here is that any critical point will actually also be a smooth function, right. So that is part of the claim that I am making. Next, for the energy for the length functional, gamma is a critical point of L if and only if there exists a reparametrization gamma tilde such that the reparametrization is a geodesic. So let me just remark that it is understandable that the statement for the being a critical point of the length functional is slightly more complicated. Again this goes back to the fact that the length functional is independent of reparametrizations. On the other, so for instance if you have a critical point, any reparametrization of it will also be a critical point, right. On the other hand a geodesic always has unit speed, right. So it is understandable that any if you take an arbitrary critical point of the length functional, it will not be a geodesic because it may not have constant speed, right. But on the other hand this says that you can always reparameterize so that it now becomes a geodesic, right. So that is the statement of the claim. So let us first prove the first part, or let me just first prove that that 1 implies 2. Okay, so then it all reduces to just proving part 1. Well, just take an arc length parameterization, just let gamma tilde be a reparameterization with unit speed. Okay. All right, then any variation of gamma of little gamma will obviously gives us a variation of gamma tilde. Why is that? Since one can just take gamma tilde of s comma t tilde to be gamma of s comma phi of t tilde, okay, where phi is the function that is used to reparameterize your curve. Okay. All right, so then now if you take the derivative at s equals 0 of the length functional, well, that is going to be the same as the derivative at s equals 0 of the length of gamma s tilde, because each gamma s tilde is a reparameterization of gamma s. So, the length functional remains unchanged, right, but because gamma tilde is now reparameterized to have unit speed, the derivative of the length functional is the same as the derivative of the energy functional, okay, and this is 0 because gamma is a critical point. So, gamma is a critical point of the length functional, right, which means that gamma tilde is a critical point of the energy functional, which means by 1 this is equivalent to the statement that so in fact all of these are sort of equivalent, this is equivalent to the statement that gamma tilde is a geodesic, and we are done. Okay, so the second part is clearly a consequence of the first part. So let us now prove the first part. Okay, so right, so this part is easy. Suppose gamma is a geodesic, then clearly right. Why is that? Let me go back to the formula of the first variation. So if since we are anyway dealing with proper variations, the boundary terms will not contribute. Next, gamma being a geodesic is already smooth, so these terms coming from the jump in the velocity vector of gamma will not arise, and then gamma is a geodesic, so the intrinsic acceleration is 0. So all three terms in the first variation formula cancel, and we clearly have that that this is true. Okay. So clearly a geodesic is a critical point of the energy functional. Now let us prove the converse, that is the hard part. So suppose gamma is a critical point for the energy functional. So the proof consists of 3 steps. So the first step is that gamma is a broken geodesic. I.e., for all p t not equal to ak. So, at all the smooth points I claim that the intrinsic acceleration is 0. Okay. So, that means at least on the smooth parts your gamma is actually a geodesic. Okay. Right. So, so if not, then there exists a k and a t naught in the interval ak minus 1 to ak, such that the intrinsic acceleration at that point is not 0. Okay. But then by continuity, because in a neighborhood of this t naught your gamma is actually smooth. So, in particular the intrinsic acceleration is continuous. So, by continuity there exists a delta positive such that if you take the norm of the intrinsic acceleration, this is never 0 on the entire interval, let us say t naught minus 2 delta and t naught plus 2 delta. Okay. Also without loss of generality, by choosing delta to be really small, we can assume that this entire closed interval is contained inside ak minus 1 to ak. So, that gamma is smooth on this entire closed interval. Okay. All right. So, now what is our goal? We want to construct a proper variation gamma of St with variation vector field V of t, which is only supported in this interval t naught minus 2 delta to t naught plus 2 delta, and such that V of t is given by the intrinsic acceleration on, let us say, a slightly smaller interval t naught minus delta to t naught plus delta. Okay. So, how do we accomplish this goal? So, let me draw a picture. So, here is your t naught, let us say this is our interval ak minus 1 to ak, this is our interval t naught minus 2 delta to t naught plus 2 delta, and I have a smaller interval here which is t naught minus delta to t naught plus delta. So, the idea is that you simply take a cutoff function which is 1 here, and so this seems like a corner, but I want a smooth function. Something like this. Okay. So, let chi be a smooth function on R such that the support of chi, which by definition is the set of all points t such that chi of t is not 0, and the closure of this, I want this to be contained inside this interval, and I want chi to be positive between 0 and 1, and chi is identically equal to 1 on the smaller interval. Okay. And then we just take let V of t be chi of t times the intrinsic acceleration. Okay. Then clearly the support of V, because the support of chi is in this interval, the support of V lies in this interval. Now the only part is why does capital V arise as a variation vector field of a proper variation. For that here is my claim, and I will only I will not prove this completely, but I will indicate how to prove this. It is a good exercise to try to write down all the details. So there exists a proper variation gamma of little gamma such that the variation vector field of capital gamma is precisely this V of t. So later in I think next couple of lectures when we study the exponential map, we will actually get a very general way of constructing such variations, but for now one can actually just do a local construction. So the proof is let us say you have this curve gamma, you have this point t naught, and you have this interval t naught minus 2 delta, t naught plus 2 delta. So by choosing again delta small enough, I can assume that this entire thing is contained in a coordinate chart. So this is a coordinate neighborhood. Okay, so that a neighbor I mean by transporting by this coordinate chart, you can think of this as a subset of Rn, right, and then you have this this variation vector field here. To construct a variation which becomes 0 at these endpoints, to construct a variation you simply traverse this along this vector field in straight line paths, and these become shorter and shorter as you approach the boundary of the interval, and then beyond this interval you just keep gamma fixed, right, capital gamma fixed. So you do not do anything outside the neighborhood. Okay, so this clearly helps you construct a variation capital gamma whose variation vector field is given by V of t. So now apply the first variation formula. So by the first variation formula, along this proper variation, if you compute the energy, then because gamma is a critical point, this is going to be 0. On the other hand, by the first variation formula, you basically get right. So maybe let me just write down the first variation formula quickly. Right. So now because you are dealing with a proper variation, these two terms will cancel out. Also the thing to note is that V at each of these problem points is 0. Okay. Why? I mean that is by construction, because this interval is completely contained inside in the area where gamma is already smooth, right. Outside of this V is 0, so all of these terms will be 0. So you are only left with the integral, but the integral is also 0 outside of this interval. So this is just going to be minus the integral from t naught minus 2 delta to t naught plus 2 delta. Okay, but now I just plug in what V is. So remember V was this cutoff function, the bump function times this, which means that we get this identity that 0 equals this integral times the intrinsic acceleration squared. Now by assumption this is strictly positive, right. On the other hand, this is non-negative with chi identically 1 on this interval, right, which means that when you integrate, this quantity is strictly less than 0, and of course 0 cannot be strictly less than 0, so that is a contradiction. Okay. So, the upshot is that we have now shown that at least on the smooth parts your gamma is actually a geodesic. Okay. So, the second step is to show that in fact the jump in the velocity vectors are all 0 for all k. Okay. Again we argue by contradiction, it is a similar proof. So, if not, then there exists a k such that if you take the norm squared of this is strictly positive, right. But then as in the previous step, we choose a delta such that if you take a delta neighborhood around ak, then that does not contain any of the other non-smooth points for all j not equal to k. Okay. So, you have your ak here, you take a little interval so that the rest of the problem points are sort of outside. Okay. And now simply take again take a bump function chi which is smooth on R such that again chi is between 0 and 1, chi is identically 1 on ak minus delta ak plus delta, and chi is 0 outside, sorry, maybe I can take a delta so that aj does not such that aj does not belong to ak minus 2 delta to ak plus 2 delta for any j not equal to k. And let v of t be simply right. So I have to be a bit careful. So let delta small enough such that the entire piece the closure of this interval under gamma is contained inside U, where U is a coordinate neighborhood with coordinates x1 up to xn. So suppose this jump in the velocity vector is given by some vi times del I at this point gamma of ak, right. Then consider the vector field x on this coordinate neighborhood whose components are given by these constant functions vi. So it is vi del I at x. Okay. So that means at the point gamma of ak, this x is just given by the jump in the velocity vector. Okay. And now simply take v of t to be x of gamma of t times this cutoff function kappa of t. And as in the previous step, we construct a variation with this as the variation vector field. Okay. And now apply the first variation formula. Again, because v of t vanishes outside this small interval, I can always by the previous construction, gamma, capital gamma will now be a proper variation again. So one can apply the first variation formula. So 0 is d by ds for this new variation, but again by the formula in the first variation formula there are again 3 terms. The boundary terms will cancel because this is a proper variation, the integral will now cancel because you are working with a broken geodesic. So the intrinsic acceleration vanishes on each of these subintervals where gamma is smooth, so all of that vanishes. You are only left with the terms coming from the possible jump in the velocity vector, okay, but v of aj is 0 when j is not equal to k, and when it is equal to k it is precisely the jump in the velocity vector, okay. So that means that 0, all the terms here will be 0 except the term when j is equal to k, and that will give you minus this squared, okay, which is of course strictly negative. So again we have 0 strictly less than 0, that is a contradiction, okay. So the upshot is, till now the first 2 steps have proved the following, that gamma is a broken geodesic with no jumps in the velocity vector. That is what the first 2 steps have accomplished. So the final step is to show that gamma is smooth. Okay. Why is that the case? That is because the jump in the velocity vector being 0 implies that gamma dot of ak minus is the same as gamma dot of ak plus, okay. Let us call this vector as some v. So this is a vector in the tangent space at gamma of ak. Now just imagine the following, you have this interval ak, you have this ak minus 1 and you have ak, right. Now let gamma tilde or let sigma be a geodesic from ak minus 1 to ak plus 1 such that sigma of ak, so I am specifying the initial conditions at this point, sigma of ak is given by gamma of ak and sigma dot at ak is given by this vector v, okay. But gamma restricted to ak minus 1 to ak is also a geodesic with initial conditions so let me call this maybe gamma k minus 1 with initial conditions gamma k minus 1 at ak is gamma of ak and gamma k minus 1 dot at ak is equal to this vector v, okay. But then by uniqueness this implies that sigma restricted to ak minus 1 to ak is the same as gamma restricted to ak minus 1 to ak. But similarly sigma restricted to AK plus 1 is also going to be the same as gamma restricted to AK to AK plus 1. But sigma is smooth on the entire interval by construction, because it is a smooth geodesic on the entire interval AK minus 1 to AK plus 1. Oh, sorry, I should go back and say that because geodesics only have local existence. So I have a geodesic on a small interval around AK for some delta positive, okay, and then you just consider gamma on the interval AK minus delta to AK. It satisfies this, it's a geodesic satisfying these two initial conditions, which means that sigma on the interval AK minus delta to AK agrees with gamma on the interval AK minus delta to AK. Okay. Similarly, we can do it for the other interval. But then by construction, gamma is smooth on this entire interval, because it's a smooth geodesic, right. So this means that in particular gamma is smooth on this interval. So now you can do this for each of the problem points AK, and so in particular gamma, so gamma is a smooth geodesic, and we are done. Okay. So this completes the proof of the corollary. Okay, so let me end the lecture with the following corollary, following consequence is that let gamma be unit speed such that if you take the length of gamma, it is a minimizer. So it is equal to the infimum over the set of all admissible paths from P to Q of the length of sigma. Okay. So then the consequence is that gamma is a geodesic. Okay. So that means the moral of the story is that if your curve is length minimizing, then this implies that it is a geodesic. But unfortunately the converse is not true. So there are geodesics that need not be length minimizing. As an example, we just take the sphere, let us say this is the north pole, this is the south pole, then we have seen that all the geodesics are basically these great circles, okay, and it sort of goes around the back from the south pole to the north pole. Now imagine you have a point, so just take the north pole to be P and you have a point Q here. Then if you take this geodesic from P to Q, that is clearly a geodesic, but it is not length minimizing, because the length minimizing path will be the geodesic from the other side. Okay. So all geodesics need not be length minimizing, okay, but on the other hand length minimizing curves are always geodesics. Alright. So so that finishes this lecture. For the next few lectures we are going to explore at least locally we are going to try to prove a converse. So at least so we are going to introduce the exponential map, and then using that we are going to prove a sort of local converse that that locally geodesics are actually minimizing, but then globally of course as we have seen this example they need not be length minimizing. Alright, so that is it for this lecture. I will see you, thank you for your attention, and I will see you in the next lecture. Thanks.